Alright, part 2 of the electronic products revision, Death by PowerPoint. Here you go. This one, right, this first question, oh by the way I apologise if the sound was really quiet on the last video. I think I had the microphone a bit too far away from me, so you'll have to just turn your speakers up I guess. Right, let's have a look. Now, on this one, what I'm going to do, you've done this in class, going to show you a circuit. The circuit you see will be one of these 10 options here. So I'll give you 2 seconds before I tell you the answer. So watch it, pause it, guess it, go. Okay, that's number 5, Deca Counter circuit. That is number 8, a latching circuit. That is number 10, an OR gate. That is number 2, monostable timer. It's got the switch on pin 2, remember it. That is number 9, an AND gate. Both switches have to be on for the LED to come on. That is a comparator built with an OpAmp. This one's number 1, which is the A-stable timer. That is number 6, we're using a relay to reverse the direction of a motor. This one, I've made a slight mistake on here, I do apologise. It's the closest answer is inverting amplifier, although technically I've connected it wrong, I've connected it to the wrong leg, so what I've actually drawn is a non-inverting amplifier, although the layout is the same. It's just if this was connected to the minus leg instead of the other way around. Watch the video on them if you're unsure. Next. I apologise for my bunged up voice, by the way, I'm full of cold. This would be a dark detector. Cold and dark in the basement, warm and sunny on the roof. But obviously it's on the floor, so it's a dark detector. Okay, alright, this one, I will suggest you pause it and write down which number statement you think goes with each component, and in a couple of seconds I'll show you the answers. But obviously, pause the video. Duh. Right, here we go. Okay, next, same deal, pause it now. There's your answers. Next one, and do the same thing again. Pause it now, match up the numbers. There we go. Okay. Right, sort the following into categories: input, process, output. So I'll just move by them one at a time and tell you. 555 timer, process, Thyristor, process, LED, output, LDR, input, motor, output, OpAmp, process, reed switch, input, relay is a process, potentiometer, input, Thyristor, input, and that's an analog input by the way, phototransistor, input, push to break switch, input, field effect transistor, process, bipolar transistor, process, AND gate and NOT gate are both processes, buzzer is an output, microphone is an input, and an opto-isolator is a process. Next. Right, draw some pictures. For my students, there's a PowerPoint on the difference between surface mount and through hole. You need to know. That would be the sort of diagram I'm expecting. The only thing missing from these diagrams is the solder, so you should have solder under here for the through hole method, and the surface mount method, the solder would be between the leg and the copper, and it's on the same side. This is how all modern electronics, or pretty much all of it, is built. This is old hat, this is sort of 1960s, 70s way of building things. Next, which statement's true? Your answer is B, produces a constant pulse. Next one, statement's true. So answer A, makes a single pulse, which is true. By the way, I never claimed any of this would be exciting or interesting. So, I'm sorry. You know, but hey, it's revision. I had to do this when I was your age, it's dull as hell. But one day, you'll grow up and life will get a bit more exciting. That's a lie. No, really, it gets better, I promise. You have kids and stuff, they're great. They cry all the time. Changing nappies, that's a riot. Anyway, sorry, I'm rambling. Right, an OpAmp comparator does answer B. Compares two voltages, can be used to show which is larger. This would be an inverting amplifier, amplifies and makes it with reverse polarity, so that is C. Next. Which one's the latch? You decide. That would be C, the thyristor. That's the symbol for the thyristor. Anode, cathode, gate while we're here. Anode, cathode, collector, base, emitter. Can't be theorist. I apologise to any Irish listeners out there. I seem to have upset Americans already, so why not Irish people? I do apologise. Oh look, that's my... No, let's not do it again. Which is the correct layout? Collector, base, emitter. There we go. C, B, E. So, answer C is the correct one. Next. Oh god, this one's dull. What does a Deca Counter do? Does that? What is a pulse? Do you know? You do now. What does the 4026 Deca Counter do? You could watch the video if you have nothing better to do. Puts it on a 7-segment display, basically. Right, next one. It resets when you put a high voltage on reset. What causes one to count? When a switch from high to low is received on the clock pin. That's voltage I'm talking about there, high voltage to low voltage, otherwise known as a pulse. It has a decoder, so it can put the count onto a 7-segment display to enable or disable the chip. Sending one of its outputs around to reset. Again, watch the video on counters if all of this seems alien to you. Lap counter, dice, random number generator. Okay, this is just a quick recap as I said. Right, explain them. What does this one do? Pause it, see if you can write it down. In fact, there's your answer. Basically, every time you push the button, it cycles through the next LED. When you press between number 9, when you press it again after number 9, it just cycles back around to the start. Next circuit. I threw these two in because it's 2016 when I'm recording this. Your exam theme is games that test hand and eye coordination. These are two steady hand game circuits made with Deca counters. On this one, this would be the track and the wand. When I touch the two together, simulated by pressing the switch, I lose a life every time. So I've got 1, 2, 3 lives. My fourth touch, if you like, will turn the buzzer on via the transistor. So on the fourth life, I'll get a buzzer sounding. At any point, I can press that button to reset it. This one is exactly the same as that, only if you pause it and look for a difference, and now you've unpaused it, I hope, you will see it's got 1, 2, 3 thyristors. So in this circuit, every time I lose a life, the lights will not only light, but it will stay on and stay on, so all 3 lives will stay illuminated as I lose them. The only way to reset this one, however, because of the thyristors, is to put a push to break in near the battery to completely cut the power by pushing it, and that will reboot everything. So technically this reset feature is actually redundant. Anyway, there are some good circuits to get familiar with, I guess. If you've got Circuit Wizard at home, if your school supplies it to you, I know mine does, then maybe build those if you're not sure what they do. Next. Okay, this shows an astable timer sending pulses to a Deca counter. So when this switch is flicked to enable the Deca counter, this circuit will basically cycle through the LEDs on its own. I won't need to hit any buttons, it will just stream through them. The reason I've thrown this one in, this could also be a reaction hand-eye coordination. If you made, say, this middle LED green and the rest of them red, you could have a circuit where you've got to hit a button to pause it on the green light. So it's kind of like a reaction tester. That might tick the box as well. In reality though, I've no idea what the exam board are going to give you. I don't know. Right, let me just check the time. How are we doing? 10 minutes, and we've got only about 15 to go. Okay. This is the other type of Deca counter you may get asked about. This is a 4026 with a decoder. Every time you push the button, you send a pulse. However, those pulses, rather than getting displayed as a single output, as in 0, then 1, then 2, then 3, it converts whatever pulse number it's on into the right legs to display it as a character on the screen. So if you imagine, if we lit up channels B and C, I'd display the number 1. If I lit up D, E, G, B and A, I'd display the number 2. If I lit up all of them, I'd display the number 8, etc. Okay, so this may come up. You could make a steady hand game out of this as well. It would just show your lives lost as a numerical digit rather than LEDs lit up. Again, watch the Deca Counters video if you're unsure. Right, link 'em. Which goes with which? Pause it, see if you can guess. And your answers should be that. Bear in mind, some of these can also be used in mass production. It's just this one is very much only for mass production. We only use injection molding in mass production because it's really expensive to make the molds, basically, because they're made out of hardened steel. They cost a lot of money and time to make, and it's just not worth it for small batches or single products. This is where 3D printing has saved the day in schools. Alright, pause it, and then I will come back and I'll circle and tell you the faults. So pause it. Right, here we go. So you've got a fault here. The plus label is joining the two legs of the LED. Here the two components are physically overlapping, so when you put them on the board they wouldn't share the same space. This is bad practice. You shouldn't really put a very thin track through the middle of this, particularly not at school anyway, because our equipment can't etch circuit boards to that quality. In general, there's a lack of labels. There should be far more component labels. We've got a track not connecting here. We've got very thin pads for this chip compared to the size of the hole, so they'd be hard to solder. We've got wonky tracks over here. We've got tracks that are too close. They should have a bit more gap between them. We've got the positive and negative connections for the battery have got a giant short circuit, so this circuit would never work. And the border is actually joining the positive and negative, or positive and 0 volt rails together as well, which would cause problems. And you've got a connection here. There's probably a few more I've missed, but if you've spotted at least 6 of those, you're doing well. Next, how is a breadboard connected? Pause it, see if you can remember. And where would you put a circuit and a battery? Right, there's your answer. That's how they're connected. The top 2 rows are joined, so this hole is connected to all of those on the top row. Same with the bottom 2. This hole is connected to those. They are not joined across this way though, be careful of that. They're only joined horizontally. And all the ones in the middle, every single one of these are joined in vertical strips of 5, as shown, but with a gap in the middle. You would put a chip like that. This way, if you think about it, every leg has individual connections. It doesn't share its leg with any other leg, if you like. They're not in the same connection holes. And where would you put a battery? Generally you'd put positive on the very top rail and 0 volts on the lowest rail, like you would if you were building a building a circuit on the screen. So, okay, next. What's that? Okay, your answer, this is known as Vero board or strip board. It's just pre-drilled strips of copper on a piece of plastic, and you can make permanent model circuit boards out of it. So unlike breadboarding, where if you wanted to take this out into the real world and use it and test it in an actual operating environment, all the bits might fall out of the breadboard. This is permanently soldered, but as you can imagine, it's a bit of a pain to change things around or make alterations or fix mistakes because everything is hardwired in. But it's very popular with hobbyists. Next one. What do all of those stand for? Pause it, see if you can guess. Answers are coming up. Here we go. This one, by the way, sim just means getting computers to kind of talk to each other, so sending data from a computer to a laser cutter, or emailing files, or video conferencing, anything where we use computers to help us manufacture and design products where they're kind of integrated with us. Or it could be computers on a production line, I don't know, checking parts for quality, taking measurements, taking photographs. CNC, computer numerical control, is what CAM machines use to move. So this basically means computers using numbers to move to different coordinates. That's how the laser cutter, the 3D printer, CNC mills all work. Dual inline, that just refers to when you buy chips or integrated circuits, they come with two parallel sets of legs, dual legs. You can buy resistors and other components in single inline format, which means they all share a common leg. Watch the thing on resistors if you're not sure about that. And hopefully the rest of them you know. IC is just the proper name for what we call a chip, an integrated circuit. Okay. Difference between QC and QA. Quality control is the checks you do to a product when it's on the production line to make sure it's not too big, not too small, that it works, etc. Whereas quality assurance is the plan, the stuff you plan at the start, to make sure you don't have many quality problems, and also to plan the checks you might do. I don't want to spend ages on this, so hopefully you know all those. They love to chuck in a couple of acronym questions, particularly push to break, push to make, etc. Right, link the flowchart symbol to the description. Okay, if you went diamond is your decision, start or stop would be the kind of oval, output will be the parallelogram, and a process or an instruction will be the rectangle. So things like weight, add, divide will go in there. Things like is switch on, is switch off, is sensor in darkness, is sensor in light will go in that. Things like turn on LED, play sound, turn off speaker, all of those things will go in a parallelogram. Okay, and start or stop. Could you write a flowchart to do that using the shapes from this page? Yes, you can. You should be able to. You've all done it for your coursework. Well, if you're one of my students, you have. Here you go. This would be the sort of thing we're looking for. There will be a pick chip question almost certainly. I imagine it will be about a steady hand game or something similar, probably turning lights on or off when a button or something's pressed. Make sure you use the name of the input and output that's being called. So on here my switch is connected to D1, my LEDs are on Q0, Q1, Q2, Q all the way up to 7. So make sure you use the correct words, make sure you draw arrows, make sure you have two paths for decisions, a yes and a no, and comment it as well. Put annotation on it to just in case the examiner doesn't understand your kind of flowchart code language that you've used. Alright? Next. Could you write down how to vacuum form in 5 stages? Pause the video and go do it. And now you're back. You should see this. Put the mould in the chamber. By the way, make sure the mould has sloped sides, rounded corners and no overhangs. Clamp plastic sheet above it. Pull the heater across. Remove the heater. Push the mould in as per the pictures, okay? I would expect you to draw these diagrams. Mould in, clamp the sheet. Heat the sheet until it sags. Press the mould up into it and apply the vacuum, and then the 5th picture that's not shown is you lower the mould, switch it to blow so it's easier to remove the mould, and unclamp and take out your finished part. There's plenty of videos on the internet of how vacuum form works. You will get a kind of essay question. There's more than likely going to be a question about a production or manufacturing process in there somewhere. It might be 3D printing, because that's quite a popular topic at the moment. If you're going to describe how 3D printing works, there you go. Read that, pause it, memorize it. Okay, next. There will be a discussion question. It might be like this. So if you're talking about 3D printing, what do you think the advantages and disadvantages are? Pause it, see if you can come up with some and compare them to this. Okay, next. Injection moulding, always a popular one. Draw the machine, explain the processes. There we go. Pour the pellets in the hopper, mix them up, melt them with the heater, which is wrapped around the cylinder, squeeze the liquid molten plastic into the mould, let it cool, open the mould, and pins push the plastic part out. Okay, again, plenty of videos on YouTube land of injection moulding if you want to find out how that works. This would be a mass production process. This is how all modern plastic parts and electronic cases are made. Right, miniaturization is a topic. Name some modern technologies that have allowed for it. So, computer-aided design has allowed us to make products ever smaller because we can plan and draw much quicker and better and closer together on a computer than we can by hand. So automation, pick and place machines, Google that, it's quite cool. Also allows us to make things smaller because we don't have to pick them up. Surface mount technology, all modern circuit boards are built this way because they're smaller and they're quicker to assemble. Nanotechnology, if you look up things like MEMS and processors and how integrated circuits are made, you'll see that we can make components ridiculously tiny, almost on the nano scale, which means 1,000 millionths of a meter. Tiny. So nanotechnology is a buzzword. Technically this should say reflow soldering, I do apologise, but reflow soldering is the method we use to solder really tiny surface mount components, so we don't need a bloke with a soldering iron, or a girl with a soldering iron soldering things. We can do it all in one hit, so Google reflow soldering if you're not sure what it is. And integrated circuits, these have been around about 50 years now, but squeezing lots of components onto a chip that do a job saves us having to find and put all those components together on their own. So this is something you can talk about, right? There's going to be an SMSC question. There will be one of these in there. It could be something like, explain how mobile phones have benefited and caused problems for teenagers, or explain how electronic products have or how they have affected the environment. There will be something like this in there somewhere. So my question as a topic one, just to get you practicing, why is making products smaller better for the environment? There's a good argument. There's another good argument. That's also true. Okay, this is a moral one. Alright, modern communication, thinking your mobile phone allows people to stay in touch. That's a social and moral benefit. And the fact we can carry those devices on us is also good for security and for navigation and for help. Okay, and you could talk about how the technology is also helping in medicine, making people live longer, etc. I'm sure most of you have got enough common sense to answer that question. Right, my final bit of advice then. There will be a big design question in the paper somewhere. This is the one that is worth a lot of marks, and people, well, in my experience, my students always tend to mess it up slightly. So just read this advice and see if you can try and recall that when you do the question on Tuesday. Read it. Quite often you will find you have to answer the question in stages, and if you jump the gun, so to speak, and answer part one in a particular way, you may then find when you get to part 2 or 3 that you wish you'd done part 1 differently, because part 3 relies on part 1, if you see what I mean. You'll know when I get there. So read the whole thing first and develop a plan of what you might answer for each topic and make sure they link. This bit everyone seems to forget. Think about where it's going to be used. A few years ago there was a question on designing something that's strapped to the underside of a model aeroplane to detect when it landed in a field. And the number of people, when I did it as a mock exam a few years later, that just drew massive, great flat boxes. No one thought about the fact it needs to be lightweight, super aerodynamic, very low and sleek and thin. The fact that it needs to actually bolt onto an aeroplane somehow. None of them thought of this. So think about where it's going to be used, who's going to use it, and what it's got to do. That will influence what shape you should be drawing. This is probably one of the most important. At the top of the question, particularly the drawing part of it, will be 4 or 5 bullet points saying things like show where your components will be placed and justify why. Explain what materials and processes you will use. Show how you will gain access to the box and where the battery will be located. There will be a list of things like that. The number of people that just seem to ignore those bullet points and just start drawing and don't bother to include that detail. You should have something to tick every word of every bullet point. That's where you're getting your marks. If you don't do that, you're a muppet. Look at the marks available. Quite often some will give you, if it's just 1 mark, they're probably just looking for a 1-word answer. If they've given you 4 marks, they're looking for a reason, an example, some justification, an argument to back up your point, so make sure you do that. Do explain what materials you're going to use, and don't just go wood, metal, plastic. Actually name a particular one. Say, I'm going to use aluminium because it's lightweight and easy to shape, or I'm going to use acrylic because I want it to be transparent and have good optical properties. Explain how you're going to make it. Are you going to vacuum form it, 3D print it, injection mold it, laser cut panels and glue them together? What are you going to do? Annotate everything. Seriously, and this goes for the whole paper, but particularly the design question. Annotate the hell out of everything. Every single thing, no matter how small it is. Sorry, I'm really starting to suffer here. Chances are some of you will draw very badly, but actually that doesn't matter. If you are good at annotating and can explain what your horrendous drawing is supposed to be with words, you'll still get most of the marks. And then finally, go big. Some of you seem to draw everything tiny and you can't make out any detail, so draw your pictures larger. Do use a ruler where possible. Don't spend forever on it, but you do get marks for communication. Right, now as I'm starting to lose my voice and about to have a coughing fit, that's the end of the video. Good luck. I would love if anyone's made it this far. I was trying to work out the other day, I went on my analytics for YouTube, and apparently only 8% of my traffic is coming from people who are in the age range that I'm trying to teach. So either that means everyone who's a year 11 student is lying about their age for YouTube. Why you would do that, I don't know. Or people watching my videos are just old geezers like me, and people from foreign countries. So if you are a UK student studying electronic products, leave me a comment, a nice one, and I just want to see how many of you are really students out there. That'd be cool, because I'm getting a little bit depressed in this subject. The government's killing it off in a couple of years' time. You know, I just want a bit of an ego boost, really. So anyway, good luck with your exam, and yeah, see you later.